Dear students, how to use graphical method to solve linear programming problem. So let us discuss in this video. So I have posted one more video for graphical method in my channel. So this is the second problem I have considered. So in this problem it is required to maximize z is equal to x1 minus 2x2. So the objective function is z is equal to x1 minus 2x2, which is to be maximized. So the decision variables are x1 and x2, which are subject to the constraints minus x1 plus x2 less than or equal to 1, 6x1 plus 4x2 greater than or equal to 24, 0 less than or equal to x1 less than or equal to 5, and 2 less than or equal to x2 less than or equal to 4. Okay, so to follow graphical method we have to represent all the constraints in the graph, but we cannot directly represent an inequality function in the graph. So for that we are going to follow the ideology, that is, we cannot directly represent or draw this inequality in the graph, but we are going to draw minus x1 plus x2 is equal to instead of less than or equal to 1. So now we can draw this line in the graph. Then by considering the line, that is minus x1 plus x2 is equal to 1, and the portion below this line, that is less than or equal to 1. So combinedly, by considering the line and the portion below the line, we can represent this inequality in the graph. So this is the ideology. Okay, so let us do the process one by one. So for drawing a line using a linear equation in the graph, we need at least 2 points to represent a line in the graph. Okay, so for the first case, that is minus x1 plus x2 minus x1 plus x2 is equal to 1. Okay, so put x1 equal to 0, then x2 will be 1. Okay, then put x2 equal to 0 for getting the second point, then x1 will be minus 1. Next, for getting the second line, that is 6x1 plus 4x2, 6x1 plus 4x2 is equal to 24. So by putting x1 as 0, then x2 will be 6. Then for getting the second point, put x2 equal to 0, then x1 will be 4. Okay, then the third constraint, 0 less than or equal to x1 less than or equal to 5. So for getting this constraint, we have to consider the line between x1 equal to 0 and x1 equal to 5. So the portion between the lines x1 equal to 0 and x1 equal to 5 will represent the inequality constraint 0 less than or equal to x1 and less than or equal to 5. Then the last constraint, that is 2 less than or equal to x2 less than or equal to 4. So the portion between the lines x2 equal to 2 and x2 equal to 4 will represent this inequality function. Okay, so now in the graph, consider the decision variable x1 along the x-axis and the decision variable x2 along the y-axis. Okay, so the axis x1 will represent the line x2 equal to 0, and the axis x2 will represent the line x1 equal to 0. Okay, so mark the coordinate positions like this. So to draw the first line, that is minus x1 plus x2 is equal to 1, already we have identified 2 points, that is 0, 1 and minus 1, 0. So we can mark this in the graph. So this is 0, 1 and this point is minus 1, 0. So by joining these 2 points we can get the first line, that is minus x1 plus x2 is equal to 1. Okay, so now to draw the second line, that is 6x1 plus 4x2 is equal to 24. So already we have identified 2 points for drawing this line, that is 0, 6 and 4, 0. So this is 0, 6 and this point is 4, 0. So by joining these 2 points we can get the second line, that is 6x1 plus 4x2 is equal to 24. And to represent the third inequality constraint, we have to draw two lines, that is x1 equal to 0 and x1 equal to 5. So the portion in between these two lines is the third constraint. Okay, so this is the line x1 equal to 0, that is the x2 axis, and this is the line representing x1 is equal to 5. Okay, okay, then to represent the fourth constraint, that is 2 less than or equal to x2 less than or equal to 4, we have to draw two lines, that is x2 equal to 2 and x2 equal to 4. So the portion between these two lines will represent the fourth inequality constraint. So this is the line x2 is equal to 2, and this is the line x2 is equal to 4. So the portion between them represents the fourth constraint. Okay, so now all the constraints have been represented in the graph. So considering the first constraint, minus x1 plus x2 less than or equal to 1. Okay, so we have drawn the line minus x1 plus x2 is equal to 1. So the line, so the portion below this line represents the solution space. So the second constraint is 6x1 plus 4x2 greater than or equal to 24. So we have drawn the line 6x1 plus 4x2 is equal to 24. So the portion above this line represents the actual constraint given in the problem. Okay, and the third constraint, the solution space is in between the lines x1 equal to 0 and x1 equal to 5. Okay, so this is the solution space, and the fourth constraint represents the solution space as in between the lines x2 is equal to 2 and x2 is equal to 4. So by considering all the constraints, we can draw the solution space like this. Okay, so in the solution space we can mark the vertex points. So this is point A, point B, so this is a vertex C, D and E. So the coordinate positions for the vertex points, so the point A is the intersection of the two lines 6x1 plus 4x2 is equal to 24 and x2 is equal to 2. So by solving these two line equations, we can get the coordinate positions for point A as 8/3, 2. Okay, the point B is the intersection of the two lines x1 is equal to 5 and x2 is equal to 2. So the coordinate position will be 5, 2. The point C is the intersection of the two lines x1 is equal to 5 and x2 is equal to 4. So the coordinate positions 5, 4. Point D is the intersection of the lines minus x1 plus x2 is equal to 1 and x2 is equal to 4. So by solving these two line equation, we can get the coordinate positions for point D as 3, 4. And by solving the two line equations, 6x1 plus 4x2 equal to 24 and minus x1 plus x2 equal to 1, we can get the coordinate position for point E as 2, 3. Okay, so now we are going to find out the solution for the objective function z by considering the coordinate positions for the vertex points. Okay, so vertex points and the corresponding value of z. Okay, so we know the objective function z as x1 minus 2x2. So the coordinate points A 8/3, 2, B 5, 2, C 5, 4, D 3, 4 and E 2, 3. So the corresponding z value for vertex point A, by substituting x1 value as 8/3 and x2 value as 2, then we will be arriving at the result minus 4 by 3. So the corresponding z value for the vertex point B is 1, for point C minus 3, for point D substitute x1 as 3 and x2 as 4. We will be arriving at the value of z as minus 5, and for E that is minus 4. So the problem is to maximize the function z. So the maximum value will be arriving for vertex point B. So the optimal solution for the given problem is maximum z is equal to 1, and which is achieved with x1 is equal to 5 and x2 is equal to 2. So this is the optimal solution for the given problem.